Testing, testing. Testing on Twitch. Twitch is working. Testing on YouTube. Testing on YouTube. All right, YouTube works. Let's close out YouTube. And let's test on X. Testing on X. Texting on X. Testing, testing, testing. Why is it never live on X? What is going on? Testing. All right, it's live. Works. Let's go. Let's get started. All right. Welcome to another Hoopo stream. Today we're going to be looking at some Mamba models. So the stream is called Gamba, Jamba, Cobra. I partially picked these just because the names are kind of cool, to be honest. How's it going, Cheb? How's it going, Lee Cox? But I also picked these three different papers. One of these isn't even a paper, but because they showcase how Mambas are being used across different modalities and different problem spaces. So we're going to be looking at three different things. One thing we're going to be looking at is Jamba, which is a new language model that is kind of like a hybrid Mamba transformer, but it's a big language model, so we can compare it to kind of the other big language models, and we can see some of the stuff associated with that. So that's Mambas in the language model world. Then I also want to look at this paper. This paper is called Cobra. This paper is about using Mambas in the vision language model world. So vision language models are the language models that kind of answer a question. They consume image tokens and basically answer questions from that. So we have Mambas in language models, Mambas in the vision language model world, sometimes also called MLLM, multi-modal large language models, although I prefer the vision language model terminology. And then we're also going to look at this paper. This paper is called Gamba, which is Mambas for 3D, image to 3D. So basically the 3D world, you're generating a three-dimensional representation of an object, in this case a Gaussian splat, which is one of the newer types of 3D representations that is also kind of like Mambas slowly taking over the world. So this is the first kind of combination paper I've seen there of Mambas plus Gaussian splat. So yeah, we're going to be looking at all three of these and seeing kind of where Mambas are at, you know? I think a little bit ago when we were doing Mamba streams, it still seemed like it was very academic, just kind of here and there for novelty's sake, but now we're starting to see them kind of all over the place, and hopefully we can get some insight about Mambas by looking at these. How's it going? Glass Cannon Gaming and 87GN. So maybe let's start with this one here. So, or actually, let's start with this one here. This is probably the easiest one. So this is Gamba, marrying Gaussian splatting with Mamba for single view 3D reconstruction. Mamba is the new architecture. Gaussian splatting is the 3D representation. And single view 3D reconstruction is just a fancy way of saying creating something 3D from a single view, aka a single image. So it's going from an image into a three-dimensional representation of the object in that image. And they're going to be using Mambas to do that. So Gamba is an end-to-end amortized 3D reconstruction model from single images. It uses a Mamba-based sequential network. Mambas are more formally called SSMs. So I have here the original Mamba paper. This is the original Mamba paper. I think it was actually one of these guys' PhD dissertation, but linear time sequence modeling with selective state spaces. So sometimes you'll see these abbreviated as this, SSM. So SSM is kind of the more formal name for a Mamba. And there's variants that have more S's. So I think there's S4M, there's S6M, which is like adding more adjectives that have S's in them. So structured state space sequence models, and then selective structured state space sequence models, and so on. But if you see a bunch of S's with an M at the end of it, that's effectively a Mamba. Okay. Mamba based, blah, blah, blah. They're going to use the OmniObject 3D data set as kind of the source of training data for this. This is like just a giant data set of 3D objects, but it's not actually even the biggest one. And they do mention that in the limitations here. So Gamba has only been pre-trained on the OmniObject 3D dataset, which is significantly smaller than the widely adopted Objaverse dataset. So the results for this paper are honestly not that amazing. So here you see a comparison of the Gamba, which is the Mamba-based one, with LRM TGS. I think we've actually reviewed these ones as well. So it's not state-of-the-art, but that's not the point of this paper, right? The point of this paper is to see if you can even use Mambas for this type of stuff. And the whole point of these Mambas, right, is that they're very fast. That's why they chose the word Mamba, because it's a fast snake. I don't know if Mambas are necessarily the fastest snakes, but I guess they're a type of snake, and maybe they're fast in terms of the striking speed. Maybe they slither fast. I don't know. But because of that, it's going to be significantly faster than some of these other image to 3D algorithms, and this one only takes about 0.6 seconds on a single NVIDIA A100 GPU. So here's basically what's happening. You have your single view, your input image. It's going into this block here, which they're calling the Gamba model. And we'll actually see that this is not really a full Mamba. This is a combination of transformers and Mambas as well. That will output three-dimensional Gaussians, and then you can splat those with the tile-based render in order to create more images. So the 3D Gaussians are the actual representation of the object. This is what you're kind of really interested in, but if you want to go back to the two-dimensional world and make it an image, you would just render it from some view. So let's start with a little summary of what 3D Gaussians are. So we're going to skip all this introduction section, which is kind of just generic stuff here, and we're going to go to this preliminary section here in the paper where they introduce Gaussian splatting. Each Gaussian, denoted as G, is defined by a mean, a covariance matrix, a color, and an opacity. So what a Gaussian splat is basically a set of little tiny Gaussians, and each of those little tiny Gaussians, you can kind of think of it like a little blob, right? So here you have little Gaussians. Some of them are big and fat, some of them are round and small, some of them are kind of oval shaped, and each of those little Gaussians is parameterized by a couple different things. So here you have a nice little GIF. This shows you a Gaussian. The Gaussian has a center. Here's that center mu. The Gaussian has some covariance matrix, which is basically the kind of the width and you could think of it like the radius of the ellipsoid in all the different dimensions, except what it's really doing is it's representing the standard deviation or the variance of a multidimensional Gaussian, especially a three-dimensional one. And then P is going to be the point at which you're evaluating this. So ultimately, you're going to have some novel view that you want to render, and then for that novel view, you're going to have the image plane, which is basically your pixel space, and then for each point in that pixel space, you're going to project a ray out. You're going to see where it intersects all these little bubbles or Gaussians, right? It kind of looks like this, just a bunch of little bubbles. That ray is going to intersect a bunch of them, and then you're ultimately going to render that. And the opacity, right, this alpha here, when you have a bunch of these Gaussians in a row, like the more see-through ones will allow you to see through the other ones, and then so on until at some point you can't see through it anymore. These pictures are from this 3D Gaussian splatting tutorial page. So this is a pretty great resource. I would recommend it. It's basically a talk that was given by the people that largely came up with the 3D Gaussians, and they have three different presentations here. Introductions to 3DGS, which stands for three-dimensional Gaussian splatting, 3DGS in practice, dynamic 3D Gaussian, surface reconstruction. I highly recommend this. These are very nice presentations that basically go into all the details and show you what all the different parts of Gaussian splatting are, the historical kind of background for them, and so on. If you're interested in kind of having a full, detailed understanding of what Gaussian splatting are, I would definitely recommend these resources. Okay, so that's Gaussian splatting, a nice little summary. But now let's go into state space models. So state space models are what a Mamba is, right? So as I said before, a state space model is the more formal definition of a Mamba, I guess the non-meme name for Mambas. How's it going, Ed? And what SSMs are linear time invariant system of equations that capture the dynamics of a system's state variable. So if you guys have ever seen the attention soft equation, you guys have seen this equation for sure, right? Attention equation transformer equation with a J, this one here, right? So you guys have definitely seen this before. The attention mechanism inside a transformer is largely composed of three parts here. You have your queries, your keys, and your values. You're multiplying your queries by your keys and then using that to basically select the appropriate values in this V matrix here. So if this equation, softmax of QK transpose over square root of DK times V, if this represents the attention mechanism behind the transformer, so if this is the fundamental equation of the transformer mechanism, then this equation here is the fundamental equation for a state space model or a Mamba. So you can kind of think of this as the attention equation for Mambas. And what these equations are really denoting is basically this. So let's go back to this paper. This is the original Mamba paper. They have this figure here, which I think is very illustrative. But a state space model is a sequential model that is kind of like running through your state one by one. So it's similar to a transformer where it's consuming a sequence, right? A sequence of things, where that sequence of things can be a sequence of text tokens, it can be a sequence of image tokens, it can be a sequence of Gaussian splats. It's a sequence of anything, right? The fact that you can pretty much take any modality and turn it into a sequence of things is why sequence-based models are kind of everywhere. But ultimately, these SSMs are composed of these different matrices here. You have your B of t, your delta t, your CT, and your A. So you can see that that's really the three parts here. You have your A, you have your B, you have your C, and then that delta is coming from the fact that this is a continuous time system, and you want to turn it into a discrete time system, so converting it from a continuous time representation to a discrete one. In order to do that, you basically have to introduce this sampling period delta, which is really just telling you how you're breaking down your continuous signal into a discrete signal that has specific steps. And that allows you to basically change these A, B, C, and D into A bar, B bar, and C bar, which are just a function of A, B, C, and D. And that's what you're having here, right? So your A matrix, your B matrix, your C matrix. Now, that's kind of a traditional state space model, but now, how do you get this selective part of it, right? So the selective part of it comes from the fact that, and this is really the contribution of the original Mamba paper, is that this B, this delta T, and this C are actually going to be functions of your input, right? So your input here, x of t, which is your actual state, that's going to be your actual vision token or your actual text token. You're going to actually project that, which means you're going to feed it through a little tiny layer of neurons in order to actually get this B of t. So now what you're doing is you're making this B of t, this delta t, and this C of t dependent on x, right? So now it's input dependent dynamics, right? Which basically means that now you can change what this B of t and C of t are doing based on the input, which is actually kind of similar to what happens here, right? Where the query and the keys are kind of together deciding which of the values matter, right? So ultimately what's going to come out of this part of the attention is some number, which is either going to be very small, which means that it makes the corresponding part of the values very small, or it's going to be very big. So it's kind of like selecting the parts of this V that are relevant or not relevant. So similar kind of thing is happening here with state space models where the B of t, the C of t, and the delta of t, right, are dependent on the input. So in that way, they're kind of changing or selecting which of the things in this A you actually care about. And ultimately this A, right, which is here, A bar, or this right here, is changing this HK minus 1. This HK is the hidden state. So the hidden state, you could think of it like the memory of this entire system, right? So this system is going through the input or the sequence of tokens one by one, and as it moves one by one by one by one through this sequence of tokens, it's accumulating or keeping track of kind of the history. And this history is hidden inside this higher dimensional latent state H right here. So HT is almost like kind of the memory, if you want to think of it that way. It's kind of like storing all these information that you need to make the next hidden state, and then the next hidden state. And the reason that state space models, selective state space models, are much more efficient than a transformer is that this H of t is always the same size. In a transformer, you don't really do this, right? You're taking the entire input sequence and then doing an attention computation over the entire input sequence. So you're making kind of a big giant square, right? Where the sequence times the sequence, and then that's the attention matrix. So the bigger your sequence is, you're making this square bigger and bigger and bigger, which means it's quadratically increasing with the length of the side of the square. But selective state space models, this H of t, the size of that, is constant. So you can think of it like almost like a rectangle, right? Where now, rather than the sequence length being one side, both sides of the square, one side of the square is just this hidden state, and then the other side of the square is the sequence. So now you have a rectangle, and as you make the sequence length bigger and bigger and bigger, all you're doing is just increasing one side of the rectangle. So comparatively, the area of that rectangle is going to grow linearly with respect to the input sequence size, compared to a transformer where you're increasing the size of this square, which means the area of the square is going to grow quadratically. So that distinction there between linear growth based on the proportional to the input sequence length compared to quadratic growth compared to the input sequence length is why these selective state space models are very popular. And these aren't necessarily entirely a new idea. These have a lot of similarities with some earlier ideas such as recurrent neural networks, and there's been like a million different variants of these things throughout the year. Even this idea of state spaces, right? This A, B, C, D equation is also very old, like in a lot of control theory. You also have this type of stuff. So it's more of a modern refresh of older ideas rather than necessarily something completely new that kind of came out of nowhere. How's it going, Khalil and Earthic? Sometimes try being high and then read papers. Yeah, you got to try being high and then coding. That's better than being high and reading papers. Okay. So that's a little bit about what selective state space models are and a little bit about what Gaussian splatting is. But now what is Gamba, which is this kind of combination of both of these? So what Gamba is going to be doing is they're going to start with an image, right, this single view, and then they're going to feed it into this image tokenizer. And this is a dyno. Dyno is a specific type of training which was used in this case by Meta. Meta, the company behind Facebook, they have a very good computer vision team, I guess, and they're well known for these type of using self-supervised fancy methods to create these giant image encoders that have been trained on giant data sets. So more often than not, when you see image encoders, it's usually Dyno or Clip. Clip is not trained by Meta, but Dyno is a very popular image encoder, I guess, is where I'm coming to. But that will produce a sequence of image tokens right here, which they call the condition image tokens. Then they have learnable 3D-GS tokens. I think these are kind of analogous to the almost like the position embeddings, where it's like you have position embeddings associated, you have a little embedding vector associated with each position in the sequence, and sometimes those are learnable, which means that you're pushing gradients all the way back into them. In this case, you have these kind of like position embeddings, but for each of the Gaussian splats, because ultimately the output of this Gamba is a fixed length sequence of Gaussian splats. So this green vector here is corresponding to a very specific number. I think, let me pull that number for you, 16,000. So The Gamba former consists of 16,384 tokens, each with 512 dimensions, corresponding to a 16,384 3D Gaussians. So each of these, this green vector here is a 16,000 by 512 dimensional. It's a sequence of 16,512 dimensional vectors that are ultimately turned into a bunch of Gaussians, each with some centers, some covariance, some color, some opacity, and so on. But back to this figure, the thing that immediately sticks out to me here that I don't like is that this image tokenizer here, this dino, this is a vision transformer. So this Gamba is really a combination of a vision transformer encoder and kind of like a Gamba additional encoder decoder, right? So that's kind of what I wish. When I kind of looked through this paper, I wish they would have created a image tokenizer or an image embedding model that was based on not a vision transformer, right? It's kind of sucks that they use the Dino image tokenizer. But that's actually a similar critique I have for this one as well. Maybe we'll sneak a peek into this one. This is Cobra, extending Mamba to multimodal large language models for efficient interface inference. So this is now using a Mamba for a multimodal large language model, which is just a language model that has multiple modalities. In this case, it's just the modality of vision, so it consumes image tokens and text tokens. But you can see they do the same thing here, which I think is kind of great. They use also a Dino image encoder. They also combine it with a SIG-LIP encoder. So this is a different type of image encoder trained with a different type of loss, which means that the image tokens that you get out of this are going to be slightly different than the image tokens you get out of this one. And this is a very popular technique that people use where you ensemble multiple encoders. So because each of the visual tokens in Dino are going to be focusing on slightly different semantic things compared to this visual tokens here, using the combination of both of these is going to give you more information, more signal that you can use. So multiple image encoders, kind of an ensemble of image encoders, is something we've seen many times before. But if the whole point of this paper is that you're using Mambas, why are you still using a vision transformer to do your image encoding? So kind of the same, I have the same critique for both these papers, where even though they replace part of the stack with a Mamba, in this case they add kind of this encoder part here, and then they add this decoder here, but at the very bottom of their tower is still a vision transformer encoder. And the same thing here, at the bottom of the tower you still have vision transformers. So I would have loved to see both of these papers use model architectures that were entirely based on Mambas. But maybe someone's working on that. If not, you could be the person working on that. But someone definitely needs to distill one of these vision transformer image encoders, whether it's Dino and Clip or maybe both of them, and distill that into a Mamba architecture so that the entire architecture, not just the language model, but the language model and the image encoder can be Mambas as well. Okay, let's go back to the Gaussian Splat paper. Directly supervised by the provided ground truth images and image space reconstruction loss. So this is the loss that's ultimately going to push gradients all the way back. This is going to be frozen, so they're not going to be messing with this pre-trained Dino encoder. They're not going to be doing the same thing here either. Right, so you see that little frozen means they're not touching these. The gradients are going all the way through this Mamba and then into this connector, as these are sometimes called, or projector, sometimes they're called. But this is the little piece that connects the image encoders to the language model. The language model needs basically a bunch of image tokens, so this MLP turns what's coming out of these things into nice little image tokens that can be combined with text tokens, and thus this language model just is consuming tokens as if they were text tokens, but they're secretly image tokens. But that image space reconstruction loss is going all the way through. So reconstruction loss means they're basically comparing these images with the image that you got there, basically. The image that you want with the image that you got, you take the difference between those and push that gradient all the way back. They're using the Visual Transformer Dyno V2, which is what we were saying. They're also adding this camera condition. So this is a vector that contains the extrinsic and intrinsic camera parameters. Extrinsic camera parameters are camera parameters that define the position of a camera in world space, such as the rotation and the translation of the camera. And then you have these 4 additional camera parameters that are called the camera intrinsic parameters. Here you have like the focal length, the warping, different things like that. So those are these little, this peach colored or orange colored. So you have the information of where the camera was when it took this picture. You have the image tokens themselves, and then you have kind of these pseudo position embedding type learned tokens that are basically going to be used and modified into the final image or Gaussian splat tokens that then get decoded into the actual Gaussian splats. Okay. Another kind of weak point here in this paper. This paper isn't that amazing. I think it's good in terms of like the novelty, but there's a bunch of mistakes in it. One, I don't like the dyno, as I said, but here's another one. Given the inherent unidirectional scan order of Mamba, that's not actually true. And I think in a bunch of Mamba papers that we've read, you can use multiple scan directions. So the Mamba is consuming a sequence of things, right? And that means that it'll consume the image as a sequence of tokens. So it's going to go in one direction, but you don't actually need to do that. You can actually have multiple scan directions. So we've seen that in a couple other papers where they will scan in one direction and then they'll scan in a different direction and then they'll scan maybe vertically and then horizontally and then horizontally and then vertically. So it feels like they probably should have done that rather than just have a single scan direction. They should have done one of these multi-directional scans, but I don't know, maybe they just didn't think of that or read some of the previous papers that do that. Okay, so you have a bunch of those blocks combined. In their case, the Gamba block is basically just a Mamba block, but it has this additional concatenation, which they call prepending, and then dropping, which is just has to do with dropping and adding in the camera and the image tokens, and then removing the camera and the image tokens. So it's basically just a Mamba block, but they have to add in these and then take them out at the end of the block. So a little bit potentially unnecessary. Like ideally you don't want to have these because you're not going to have these, right? The problem with these camera pose tokens is that for a data set like Objaverse, you do have the camera information. So every image in the Objaverse data set, you know exactly where that image was taken and the exact camera that was used to take that image in terms of extrinsic and intrinsic camera parameters because it's a simulation, right? It's a simulated camera taking a picture of a simulated object. But if you wanted to actually use this in the real world, you're not going to have this camera pose token information. You're not going to know which camera was used to take it or what the relative position of the camera was to the object in world space. So I generally don't like these camera pose tokens. Okay, we use a fixed number of 3D Gaussians since the Mamba blocks only support a fixed token length. And then they also do some other weird tricks in here. So this was a weird little trick that they use where they're using an object mask. One of the problems with these Gaussians is the initialization of the Gaussians. So the initialization of the Gaussians means that you don't really know where to put these at the beginning, right? So the Gaussian optimization process will eventually create the object for you out of these little Gaussians. You see, so ultimately, if you have this object, it'll figure out how to put all these little Gaussian ellipsoids such that they create that object. But the starting position for these is a little bit iffy right now. The way that people do it is usually they'll start from an earlier kind of a structure from motion algorithm, which uses multiple images to give you a good initial starting point for a bunch of these Gaussians, and then the optimization process continues from those, right? Where the optimization process is changing these values such as the center of the Gaussian. So it's moving those little Gaussians around and rotating them and making them smaller and making more see-through, less see-through. But that starting position is difficult. So because of that, they kind of put in some inductive biases here that this is going to be object-centric. They're using the object mask. So kind of, you don't like to see these little extra tricks, but I guess they had to do what they had to do. Okay, they trained this on 8 NVIDIA A100s. Blah, blah, blah. Nothing much. And the results are kind of okay. It's there, but it's not, definitely not state-of-the-art. But it is very quick, so 1 second on an NVIDIA A100. This GPU, we're going to see people use it for every single one of these papers. So whether it's Gamba, Cobra, or Jamba, all of these are using the A100. It's a very popular hardware to be using. Our Gamba does not always yield plausible results. I love this. You know, a lot of papers, they kind of feel pressure to say state-of-the-art, so they're trying to like almost like weasel their way into state-of-the-art. They find some weird benchmark in which they can say that they're state-of-the-art, but I really love the honesty here, where they basically say, hey, it's kind of not that great, but our model operates on a deterministic basis, leading to the production of average representations for these unseen region. We only trained it on a small 3D data set. We really haven't used a big 3D data set, so this is really just the start, right? It's promising and it's competitive, based on the fact that it's significantly faster than these other ones. So just the beginning, but I'm still a believer, and I feel like these Mamba models might end up swallowing the whole deep learning world, and I think this is the first part of it. So we know how to do this kind of part right here, but now we need to replace this image tokenizer with a Mamba. So the whole thing will be a Mamba. But for now, we're currently using a vision transformer with a Mamba here and Gaussian splats. So that's this paper. I don't know a lot about Mamba, but what makes it different from basic RNNs and LSTMs? It's kind of the same idea. It's just the selection mechanism here, I think, is slightly different. So there's little nuances, but it's the same kind of idea where you're kind of carrying this hidden state over and over and over and over again, right? Recurrent neural networks do the same thing. They have some hidden state that they're passing along forward. And then LSTMs, which stands for long short-term memory or long-term short-term memory or something like that. LSTMs have a kind of a similar situation, but they have like specific parts within this LSTM module that will remember long-term things and remember short-term things. They have like a forget gate. I kind of honestly forget at this point about LSTMs, but they're dealing with the same thing of like, hey, let's have a fixed length hidden vector that we're kind of putting information in and taking information out as it becomes no longer relevant. The reason this particular version is more popular now is that something about the way that you do this in GPU memory when you're training means that you can turn it kind of into a convnet, right? So one of the biggest problems with RNNs is that when you're training them and you're calculating the gradient, you basically have to have this entire sequence of hidden states like kind of loaded and go through it backwards, which means it's very slow to train. Versus these Mambas or SSMs, the way that this works out on the GPU memory, when you're training, you can almost treat it like a convnet and you do it all at the same time, so it ends up being a lot more efficient. I don't really have a better way of explaining that because it gets really intense really quickly, but if you're interested, there's a specific part of this paper here where they talk about it here. Yeah, section 3.3, efficient implementation, where convolutions are hardware friendly, and by letting blah blah blah, like there's some magic CUDA kernel stuff that requires a 500 IQ brain to really fully understand, but basically this particular instantiation of a hidden state that keeps getting passed forward is way more efficient than RNNs or LSTMs. All right. Difference is that LSTMs have fixed weights, but Mamba has contextual weights. So what Pratyush is talking about there is that the B of t, delta t, and C of t here are input dependent, which means that the values of the numbers in this B of t depend on the input here, versus I guess in an LSTM they do not. I hope you like the answer. I don't know. All right. So now we're looking at Cobra. Cobra is a linear computational complexity MLLM. extremely competitive performance, beating Lava Phi, Tiny Lava, Mobile VLM v2. This is a little bit sketch. You know, it's kind of what I was saying before, where at least these guys here kind of admit that this isn't super strong. You know, they admit that Gamba isn't necessarily state of the art. These guys are still trying to play that game where they're just going to find shittier models to compare it to. So they call it extremely competitive performance with current computationally efficient state of the art methods. So they're kind of like limiting their comparison to only these ones, but these are not really the strongest vision language models. The GPT-4V is better. You know, the Apple's vision language model's better. There's better language models. This isn't necessarily the state of the art, but they're going to kind of try to pretend that it is in some way because they want their paper to get accepted. Cobra achieves comparable performance to Lava with about 43% of the number of parameters. This is the more impressive part. So as with the Gamba paper, the impressive part with this Cobra is that because it has these Mamba blocks, it's much more efficient, much quicker than the transformer blocks. So if we go into here, transformers exhibit quadratic complexity. Cobra, being built with Mambas, exhibit linear complexity. We explore the efficacy of different fusion strategies. The fusion strategy refers to this here. So how do you create this projector in order to convert these image tokens into these tokens that can be consumed by this language model here, which is composed of 64 Mamba blocks in a row. So here's your Mamba blocks. Here we have another summary of state space models. Here's the fact that B, C, and the delta are input dependent, which means that they're a function of this X, which we see. Vision encoder, again, this is the part that I was a little disappointed by, that they just use these vision transformers, pre-trained vision transformers as the vision encoders. I really wish someone would make a Mamba vision encoder that's been distilled from Dino V2 and Siglip and Clip, because I feel like that's just waiting to happen, right? This is like the weakest link in the chain right now, is the fact that you're relying on these vision encoders here. Why not just make them Mambas and then your entire model will be a Mamba? But hey, training those things from scratch is kind of a huge pain, and it's a thankless job, so that's why nobody wants to do it. Ultimately, you combine those together, so your representation V here that is being fed into this projector is a combination of the Dino representation and a combination of the Siglip one. Okay. 64 identical basic blocks, and then ultimately you're predicting the token autoregressively, right? A language model is predicting the next token given all the previous tokens and then the tokens that you fed it here, right? So it's token by token by token by token, and the autoregressively means that it's looking at all the previous tokens that you created in order to give you that next token. The existing training paradigm for Lava, training only the pre-alignment phase of the projection layer and then fine-tuning phase of the LLM backbone, recent research has shown that this phase is unnecessary. And we actually saw that in the Apple paper. So Apple released a vision language model, and they came to a similar conclusion, where in the Lava papers, Lava is kind of one of the earlier open source vision language models. And in the Lava paper, they have this multi-stage training procedure where first they keep this part frozen, and then they keep the language model frozen, and then they only train this projector or connector. And then after they do that, then they train the full system, and then they do actually a third one where they fine-tune it. So it's like a multi-stage process. But people are realizing that you don't actually need to train this thing separately from this thing. You can just train both of these together, and that's kind of, they come to the same conclusion here. That phase is unnecessary, so they discard that pre-alignment stage and directly fine-tune the entire LLM backbone and the projector at the same time. So they're basically pushing gradients all the way through this, changing the LLM and this projector at the same time. The datasets that they use is kind of like the same mix of Lava 1.5, which has some academic VQA, Lava Instruct, Shared GPT. So a lot of these vision language models are actually kind of almost distilled from GPT-4 Vision, right? GPT-4 Vision is probably the strongest vision language model right now, but you don't have access to it. So what people do is they will feed images into GPT-4 Vision. GPT-4 Vision will create a response, and then you do that, I don't know, like 10,000 times, or in this case, 220,000 times, and then you end up with a nice little data set. That nice little data set is what GPT-4 Vision said for this image. So you fine-tune on that. Effectively, what you're doing is you're kind of distilling the intelligence of GPT-4V into your vision language model. So that's largely what they're doing here as well, in addition to some other VQA and visual instruction data sets that they have. So the entire data set is approximately 1.2 million images. Okay, you guys are still talking about LSTMs versus Mambas. How's it going, Emily, Elbadanos, Divashish? What PDF editor do I use? I use a product called Paperspace. I think Paperpile. Is that what it's called? Paperpile. That's what it is. It's a nice little PDF annotation tool. Okay, let's keep going here. The Dino V2 image encoder is a VIT large. The whole training process takes about 26.5 hours on an 8 NVIDIA A180 gigabyte. And they use the Python fully sharded data parallel with mixed precision, floating point 32, and BF16 for distributed training. It does, all right, so here you have VQA. These are different benchmarks here. You can see 77 for MOE Lava, 61 compared to Cobra here. So it's kind of, it's competitive. It's better on some things. It's worse on some things. But, you know, for being made entirely out of Mamba blocks, that's pretty good. And it's significantly faster. So do they have the speed on here? Yeah, here. This is the real metric by which these Mamba models shine. It's the tokens per second. So this is kind of the speed. And again, the reason it's so fast is because this H of T is limited. It has a fixed size. So no matter how long your input sequence is, this H of T will always be the same size. So you can think of it like that rectangle, right? The area of the rectangle is never going to, it's going to grow linearly with respect to one of those sides versus the area of a square will quadratically grow. And that's why it's way faster. You can see this mobile VLM, tiny lava. These are transformers with attention mechanisms. You see that 39 tokens per second, 40 tokens per second, compared to this Mamba 166 tokens per second. And that's 166 tokens per second still using a transformer for the image encoder. So if you made an image encoder that was a Mamba, you would get even better speed on this, especially if you have multiple images or big images, right? If you have really big images, the quadratic complexity is going to hurt you here because these are vision transformers. We use the same question as the textual prompt. Ablation study of different projection layers. Ultimately, the Apple paper that we read said that the projection layers doesn't really matter. So for a little bit, the vision language model community was uncertain about what to do with this, whether it should be an MLP. There's other fancier versions here. Like I've seen like a kind of almost like a mini ConvNet, and I've seen like almost like a mini transformer, but MLP is probably the simplest connector, right? It's just a little multi-layer perceptron. And the Apple paper actually determined that it doesn't really matter what you put here. It seems like they all kind of perform about the same. So I guess here they're MLP, LDP. Seems like it kind of made a difference to them, but for the Apple paper, they said it didn't. Oh, actually, not really. Even though this looks like a big difference, this is just 86.7 compared to 88. So it looks like it's a lot better, but it's about the same. Okay. Base model that is not fine-tuned, the model fine-tuned on the chat datasets. The fine-tuned model scores significantly higher than the pre-trained model. The base model often fails to stop, leading to a lot of repetitive content and thus affecting its performance. This is an interesting little tidbit where whenever they were training this, right, and they're training this not in a multi-stage situation where they train first this thing and then this thing, they're training them both together. They actually found that this Mamba backbone, which is a language model, if you actually start from the fine-tuned language model, right, which is a language model that is been fine-tuned to have this kind of like chat behavior, this instruction following capability, it actually is better than if you just start from the base model, which is just the model that hasn't seen any instruction tuning data set. It's just been pre-trained. It's kind of like the raw model. So I thought that was a nice little interesting tidbit there, where they found that the fine-tuned one actually works better, which is not entirely intuitive, right? You would expect that since you're fine-tuning this on a bunch of VQA type of stuff anyways, right? Maybe starting with the pre-trained model would have been better, but they actually found the opposite is true, that starting with the chat model already makes better performance. Our model has a strong ability to capture the spatial relationships of objects. I thought this was a little bit weak. They kind of try to argue that it's better at like the positioning of objects within the thing, but like, I don't know. That just seems like kind of a weird artifact. I doubt there's like something specific about the Mamba model that makes it better at doing that. It's probably just happened to end up that way just because of the particular training mix that they use, right? If you use different mixes of fine-tuning data when you're doing this instruction tuning, depending on if you have more of this type of VQA and less of this type of VQA, you're going to get slightly different stuff. So I think the fact that they had like the visual positioning or whatever they're trying to say here, where it's like the Cobra is slightly better at like determining the position of objects within the image, I think that has more to do with some artifact of the pre-training data set mix rather than necessarily some kind of inductive bias in the Mamba versus a transformer, right? I don't know. That's just my opinion, though. Conclusion, Cobra not only significantly improves computational efficiency, but also performs comparably to advanced models. This opens up new possibilities for deploying high-performance AI models in environments that require high-frequency processing of visual information, such as visual-based robotic feedback control in the future. And this is why I'm so excited about Mambas. So you guys have seen me do streams about robots before, and I've even made a little open-source robot that I was messing around with for some time. But one of the weakest parts of that little robot that I made was that the vision language model was very slow, right? It was basically like 3 seconds. So it took 3 seconds to take the image, feed it to the vision language model. Vision language model gives you the answer, and then it gives it back. And that's just way too long, right? If you're doing any kind of like robotic control where you need very fast feedback, maybe you're manipulating something, maybe you're driving a car, maybe you're moving in an environment that's changing and people are walking in front of you, you can't have a VLM that is very slow. So you need a very, very fast vision language model. So we're seeing that these Mamba-based LLMs are significantly faster. Mamba VLMs are significantly faster than the transformer-based VLM. So even if they're just a little bit worse, it's totally worth it if you're trying to do something that's incredibly requires a huge amount of speed. So I think that even if Mamba models end up being a little bit worse than transformer models on pretty much everything, the fact that they're like significantly faster means that we could still see them used in time-sensitive applications such as robotics, autonomous vehicles, and so on. Okay, that's basically Cobra. We're flying through this. I'm still a little bit sick, so I'm not trying to sit here for 2 hours and but so we're going to be kind of blasting through this. I'm reading, hey Hupo, any Mamba-based image encoder would be suboptimal compared to the LL encoders that work on all patches at once. I mean, you're kind of assuming something there, right? Where Dino is a ResNet model. Dino is a vision transformer. Dino V2 follows the VIT, which is a VIT large. So the problem with this type of vision transformer is that it's a transformer, so it's quadratic with respect to the sequence length. And in the case of an image encoder, the sequence length is the image size. So if you're trying to make this Dino V2 fast, you kind of have to resort to making it a small image. And in fact, what a lot of people end up doing is they end up taking an image and cutting it into pieces and then feeding each of the pieces separately into the image encoders. But if you had a Mamba-based vision encoder, you could probably use a much bigger image size. I don't know. That would be my pushback, Pratyush, to that. Okay, let's talk about Jamba. So this is the third one. We looked at Gamba, we looked at Cobra. Now let's look at Jamba. So Jamba is a hybrid model. This is an open source language model created by AI21 that is a hybrid of Mambas and transformers. So what it is just a bunch of Mambas stacked with transformers in between. So here you see a Mamba block, then what they're calling a Mamba plus MOE. So this is a Mamba block where you have a mixture of experts here. Mixture of experts is basically a router that routes to different MLPs or different feed forwards depending on kind of the tokens. So it is a way to have a bunch of different MLPs or feed forward layers without having all of them active all the time. So you're kind of loading them from memory. MOEs are not necessarily great for like a single GPU running inference. Usually they're more about inference, batched inference in the cloud. But, okay, so AI21, I had to look these guys up. So AI21 is an Israeli company that is on their Series C. They've raised over 300 mil, so they've actually raised a ton of money. And if you actually go and look at the different people that put money into them, 378 competitors, list this, founder profiles, funding rounds, the people that funded them, it's Pitango, Watyush. If you like look into these different funders, like Pitango is also an Israeli VC. If you look at Walden Catalyst, where do they primarily invest? Israel. So basically AI21 seems like the Israeli language model startup, and it's mostly funded by all the Israel VCs. But, okay, that's Jamba. You can see here they're comparing the performance to Mixtral, Gemma, Llama. So they're telling you that this is who they're comparing themselves to, right? So they're not comparing themselves to GPT or Claude or the closed source models because they wouldn't score that well. So they're really comparing themselves to the open source language models that are available to fine tune and use. They're releasing this under Apache 2. So they're really trying to compete with Mixtral and Llama and Gemma, which is Google's open source one. And it's competitive, right? It beats them slightly on some of these reasoning benchmarks, does a little bit worse on some of these other benchmarks. So it's kind of on par, maybe slightly better than Mixtral, depending on what you want to do with it. Fits up to 140K context, which is a big context window, right? So the advantage of the linear complexity with respect to the sequence length means that you can have a much larger sequence length, which means that your context can be bigger. So that's a little advantage there. Transformer scales quadratically, so it has slow inference. Transformer scales with context length, so it has a large memory footprint. If you have a limited amount of memory, as you do in these A100s, you want something that doesn't scale quadratically. Jamba MOE layers allow it to draw on just 12 billion of its available 52 parameters at inference, so any kind of mixture of experts means that you're only using a subset of the total model parameters. This is becoming a little bit of a meme, I think. I think people who are using these MOEs, they're using it to kind of pretend that they're like, oh, my model's only 7B, but really secretly behind the scenes, it's an MOE and there's like over 30B parameters. So there's a little bit of sketchiness here with, for example, Gemma 7B. Like Gemma 7B is, if it's not an MOE, I don't actually know if this is an MOE, but really Llama 13B, that's only 13B parameters compared to here. They're pretending that it's 12B when really it's 52B, right? So MOE is kind of becoming almost like a cheat code of like added sugars, something like that, where you can kind of pretend that there's less parameters than there are. Okay. So here we have the actual architecture, and we can see that here. So this is the AI21 Labs Hugging Face page. You can see they only have one model. This is Jamba, so you can go here and you can actually look here at this section that says safe tensors. You can click on it. So this is 51 billion parameters, and here's the parameters. So you can see it's a bunch of layers, right? You can scroll all the way down. It's exactly 32 layers. And each of these layers is alternating. You have some Mamba layers. So here is a Mamba layer, for example. Here's a standard transformer layer. The first one is a Mamba layer. So you see these A, B, C, D. That's your state space model. That's your right here. A, B, C, and then D is not shown here, but it's also sometimes it's the equation that's right here. So this would be C H of T plus D. So there's your little Mamba. Here's your DT, which is the delta. Here you have the experts, right? So in this one, right, they have this, what they call a Mamba MOE. So the Mamba MOE is just a Mamba, and then here you have a MOE as opposed to just a single MLP. So here you would have your router and then multiple MLPs. You see, and this is, for example, this is just a normal Mamba block. You see there's only one expert here. But here is a Mamba block with an MOE. So you have your standard Mamba part, which is this part here. And then here is your experts. So this is your MOE. Look at that. You have, holy shit, 16 different experts. And then your router. So the router chooses what expert to send or what expert to use. So much more extra shit, right? So even though you're only using a subset of these experts, like, you still have all these weights, right? And so you need to load them into the GPU. And so I don't know. I still think MOE is kind of cheating, but fight me on that. All right. What else do we want to talk about? Maximize the model's quality and throughput on an 80 gigabyte GPU. So this is something that they did that I thought was a bit interesting, is that they really optimized this Jamba model for the A100. And if you've noticed, all of the papers that we've looked at so far, they all use the A100, NVIDIA A100 80 gigabyte. So this is Gamba. You look at this one, Cobra extending Mamba. It's the same NVIDIA A100 80 gigabyte. Where is it? Somewhere down here? NVIDIA A100. The 8 NVIDIA is just a server rack with 8 of those NVIDIA A100s. So it kind of seems to me like these NVIDIA A100s are really becoming the workhorse of the AI world. You know, people aren't using H100s because it's very difficult to get H100. So if you're part of the startup community or if you're part of these academic communities, the best you're going to get are A100s. And just to confirm that, if you search A100 on Google, look at this. The first 6 links or 4 links are all sponsored. So you see this? Sponsored, sponsored, sponsored. What that means is that this company, Webflow or RunPod or Lambda Labs or CoreWeave, they're a company that is selling access to A100s. So, and they're trying to get your business, right? They want you to use their A100s, and so they're paying Google advertising money to put their slot here. So, you know, if I just put like a 3090 here, nobody's paying you. Nobody wants, or I guess these are maybe sponsored, but the fact that A100 is extremely competitive means that there's a lot of people trying to sell you A100s. Let's go back to this cloud cost. I think there was this one, 80% less expensive, $2.21 per hour. That doesn't seem right. I think there was one link that I found that had the actual price on it. Yeah, here you go. So 8 by A100, which is 8 of these, is going to cost you roughly $28 an hour on Azure, $24 an hour. And that's not even the real hourly price. So this is the yearly price. So the way most of these cloud computing companies work is that if you buy a bunch of hours, but a larger chunk of hours, you get a better price, right? So it's kind of like anything, right? If you buy 100 bananas, you're going to get a better price per banana than if you just buy 2 bananas. So if you buy, I guess here it is exactly, on-demand price versus yearly price, but Fluid Stack, $10 versus $11. If you click on some of these other ones, these guys are saying $8, right? And when you see that, what does that even mean, right? What does that mean? How can they be significantly cheaper? And the answer is that they're burning money, right? So a lot of these companies, FluidStack, they raised money from venture capitalists, and they need to get users, right? So they're willing to basically give you A100s at a loss. So they're losing money when you're using your A100s, but their goal is that hopefully you will then stay with them. You will build your startup on top of their cloud, and then whenever you're a bigger startup and all your software is built on top of their stuff, you will continue to use their stuff, and then they will just increase the price, and you'll be kind of locked in. But I actually disagree with this entirely, because I don't think that business model even makes sense anymore, right? Even now, we see people who kind of switch, right? So people who maybe had a bunch of AWS credits, and then you run out of the AWS credits, and then you switch and you start using Google Cloud credits. So I just don't see how any of these companies are going to survive, whether it's Webflow or RunPod or Lambda Labs or CoreWeave, right? Because at the end of the day, it's not like they're making their own hardware. At the end of they don't have their own GPUs. They're just selling you access to NVIDIA GPUs. And all they're doing is they're using venture capital money to subsidize access to these machines in the hope that you will continue using them. But what's probably going to happen is once you're done using them and the price for them sucks, you're just going to go to somebody else, right? So then what do? They just basically gave away a bunch of venture capital money for free. So I don't really understand. Maybe one of you guys works for one of these cloud companies and you have a better idea of the business model. But hey, if they're giving away A100 GPUs, you might as well use them. Yeah, they don't have enough vendor lock-in. So here's part of my conspiracy theory on this. So if you actually, if any one of you has done like kind of this cloud type stuff before, it's a huge pain, right? So like AWS, GCP, which is the Google Cloud, Azure, like it seems like the software that is used to control your instances and manage your instances in this is almost like purposefully obfuscated, right? And why would they do that, right? Why would AWS make it kind of annoying to write software to use their cloud? And I think the reason they do that is for vendor lock-in, right? If AWS and GCP and Azure were all very easy to switch to and you could get started extremely quickly, then people would just switch, and by being able to switch a lot, it would make it a competitive market, which means that they would drive the price down, right? But if it's very annoying to switch, right? If it took you a whole bunch of shitty spaghetti code to get it to work on AWS, and now you're like, shit, GCP is cheaper, but hey, dude, we spent like 2 months getting all this spaghetti code to make it work on AWS. That's enough of a hill to climb that we're not going to switch, right? So I know that's kind of a conspiracy theory, but I feel like in my mind, secretly, the reason the integration into these clouds is a huge mess and it's kind of annoying is because they want you to kind of lock it in. But here's the thing. If language models are getting better and better at writing software, and at some point, rather than you writing all this bullshit to integrate with AWS, a language model is going to do that. That means the switching cost is just going to be very small, right? Because if a language model can switch your entire backend for you and just fill out all those different JSONs with all the different configs and set up all the different orchestration stuff, then that means that you have almost no lock-in. So I don't know. Ultimately, I guess where I'm going with this rant is it seems like the lock-in argument is becoming less and less strong, and it makes less and less sense, which means that kind of all these companies that are just using VC dollars to subsidize in the hope that they have some kind of lock-in, I think these are all going to die. But hey, I guess they're giving their money to Google for advertising, and the VCs that gave them money also have a bunch of Google stocks, so they win either way. Just spent a week fighting with AWS to build a redeployable stack. Snooks, I feel you, think about that. Do you feel like the pattern was optimal, or do you think it was purposefully confusing and purposefully annoying so that you would stay with AWS, right? Think about that. Sometimes, think about it. All right. What else? Was there another stuff that I had here? I had some Gaussian splatting stuff. Oh, yeah, okay. So here's one cool thing that I found. All right, so in this paper, Cobra, right? Kind of a throwaway, but like all the way down here, they mention something. Look at this. So in this paper, they say, due to the numerical precision sensitiveness of the Mamba's recurrent dynamics, Cobra needs to maintain relatively high precision of its main parameters during inference, no lower than BF16. Huh. Okay. So I'm going to mention something here. So BF16 is a data type, right? And different data types require a different amount of memory. So you can kind of think of this as being more memory intensive. It just takes longer to use, requires more memory, kind of slow and big, right? Think about that. So 32-bit float is worse than a 16-bit, such as a bfloat 16. There's a lot of research that is coming out right now about extremely low precision data type. So we've read a bunch of these papers. I have a bunch of streams on quantization if you're interested in this type of stuff, but this is just kind of the most recent version of that. But in this paper, they created a model which uses 1.58 bits to store parameters. It's not actually 1.58 bits, which doesn't make sense, right? It needs to be an actual number. But if you take the numbers are being stored at different levels of precision, but ultimately, if you take all the numbers and average the total number of bits that they're using per number, it's 1.58. So that's why it's 1.58, but there's no such thing as a 0.58 of a bit on your computer. But that's a significant saving, right? So 1.58 bits compared to a floating point 16 or BF16, you can actually run a language model much faster, and you can look at the scores here. So Llama, a 3 billion parameter Llama language model running at BF16 takes 7 gigs of memory and runs at 5 milliseconds. The same Llama, which they say matches the performance, running at 1.58 bits, only requires 2 gigs of memory. So look at that. It's a 3 times improvement in the memory size and a 2 times improvement in the speed. Okay, but let's go back to the Mambas. It looks like this paper here, the Cobra paper, they said, hey, actually Mambas, you have to keep them in BF16. And it's like, uh-oh. And then if you go to the Hugging Face for Jamba, you scroll down here all the way to load the model in 8-bit. So 8-bit would be half the precision of 16-bit. Look at this. In order to not degrade the model quality, we recommend to exclude the Mamba blocks from the quantization. Okay, well, this is actually starting to paint a really bad picture, because now what you're telling me is that if you have this Jamba block, you can quantize these transformer blocks, but you can't quantize these Mambas. So it just dawned on to me that there might be an Achilles heel here, right? So the whole point of these Mamba models is that they're fast and that they're small, right? Is that the way that they were designed, they're basically much more efficient than transformers. But it seems to me like transformers are becoming very efficient, not because we figured out a better way to do attention, but because we realized that we can use extremely quantized transformers and not lose any of the performance. So there's a little bit of an arms race here where Mambas seem to be fast by default, but it seems like there's more and more evidence that these Mambas you can't quantize them. Basically, if you try to quantize them, they just turn to shit. So if you can't quantize the Mambas, and people are getting better and better at quantizing transformers, maybe we just end up with transformers anyways. So I don't know. I thought that was a little interesting tidbit. Maybe it's just we haven't figured out. Maybe there's just a little trick here and there that we need to do, and then we'll be able to quantize these Mambas down to 1.58 bits just as well as the transformers, in which case the Mambas would probably win. But if this turns out to be like an actual impossibility, and it turns out you can never quantize a Mamba to the tiny amount that you can quantize a transformer, that's not looking good for the Mambas. Damn, Pratyush is like, knows his shit. Look at this. 1.58 is log 3 base 2. Every single parameter of the LLM is ternary. Okay, so they're storing it in 3. And 3 possible values stored as 2 bits is 1.58. Kind of cool, man. I appreciate it. Is it possible to build a Mamba model that uses ternary weights from the start? Maybe. That's what I don't know. This could be a nothing situation, right? It could be the case that we just wait a month and somebody comes out with a paper where they quantized a Mamba to like 1.58 bits and it's totally fine. And then in that case, everything is normal. But like I said, it seems like I'm noticing a pattern here where in the Jamba you have to basically keep the Mamba blocks at BF16, and then these guys mentioned that they can't quantize it, which means they tried to do it and they couldn't do it. So I don't know. It could be an Achilles heel for these Mambas. You could try it, Joe CH. If you're looking for research ideas, definitely worth trying, seeing if you can quantize Mambas. Okay. Oh, I had this thing pulled up. So this is a DeepMind paper. This is a little bit older now, but this is kind of similar, where this is a model by DeepMind called Griffin, which is kind of similar to this Jamba. They basically mix RNNs with gated linear recurrences. You can kind of think of it like a Mamba and local attention. So they actually combine Mambas, or not Mambas, in this case it's an RNN, with a MQA multi-query attention, but it's basically the same idea as this, right? Where they're alternating these Mambas and transformer layers in order to get good performance. And it seems like there's actually precedent for that. Google did that with this Griffin model. And they also got pretty good performance, right? So here, 81 compared to 80 for a similar size here. And this is a true comparison, right? Because this is not an MOE. So this is 14B, and it's actually 14B. It's not 14B MOE secretly like 80B. But yeah, maybe, I don't know if these hybrid architectures are just fundamentally better. I think that the reason the hybrid architectures are here is because people are too afraid to do everything with Mambas, right? Like training these things is a lot of money, and training something that's just entirely Mamba blocks, it's a little sketchy, right? You're better off kind of hedging your bets and just alternating and doing these hybrid architectures. But I could see this going away. If people eventually realize that you could just do a bunch of Mamba blocks and it's totally fine, then maybe we won't need these hybrid architectures. But it seems like a couple people are trying them out and they're doing pretty good. Okay. Can't wait to see what Lamba, Bamba, Wamba, and Amba will bring us. Well, first of all, if you quantize a Mamba, it would be called Kamba. Let's actually see. Is there anything if you search for Kamba? Kamba? Quantize Mamba? Kamba IT? Kamba is a word in the Nguni language, which is the language in the south of South Africa. And what does it mean? To invent, to compose, or to make up, to name, to give a name. That's actually pretty good. So it means this is the name of the next paper. Kamba. Quantized Mamba model for state-of-the-art real-time VLM on edge robotic device. There you go. There you go. That's the next hot paper. I need to make this bigger. Quantized Mamba model for a state-of-the-art real-time VLM on edge robotic device. That's all I got, guys. I don't have a lot today. I'm a little tired. My brain isn't working 100%, but hope you guys got something interesting out of that. Maybe we'll do a little summary. Here. right, here's a summary. So today we did a stream called Gamba, Jamba, Cobra. In this stream, we reviewed 3 different recent releases of models that are using Mambas. Mambas are what are called selective state space models, and their claim to fame is that they're linear with respect to the sequence length, which means that they're basically a little bit faster, or not just a little bit, but significantly faster. They don't take as much memory as transformers. People are starting to use them everywhere. So in this Gamba paper, they use them for 3D reconstruction. They still use vision transformer based image encoder, but they're the kind of top part of this stack here, the kind of like decoder part of it, which goes directly into Gaussian splats, is based on Mambas. Performance isn't quite there, but there was other reasons why this paper doesn't have state-of-the-art, including the fact that they train on a very small data set. So a little bit of a hint of a promise there, but still not entirely sure whether Mambas are the best for that. Cobra, this was another paper we read. This is now Mambas for vision language models, or multi-modal language models, if you want to use Apple's terminology. And this one, they basically train your basic vision language model, except instead of a llama model or a Mistral model, which is what is popular for these language models here, they're now using a Mamba model. And again, they're connecting it to a vision transformer image encoder, in this case, an ensemble of 2 different ones. So they didn't go all the way, which I wish they would have. But it seems like the performance is pretty good. It's kind of comparable to your other open source VLMs. And it's significantly faster in terms of tokens per second because of the Mamba part. One interesting part, actually, let's go to this. The next thing we looked at was the Jamba. Jamba is a language model that is a hybrid language model, kind of along the lines of, for example, Griffin, which is a mixed architecture as well from DeepMind. In this case, Jamba is a mixture of transformers, Mambas, and then a Mamba MOE, which is basically a Mamba with an MOE block instead of this MLP. The performance is pretty good. Obviously, it has all the benefits of Mambas, where you have bigger context, it's faster. It's all optimized for A100s. All of these papers are using A100s, kind of confirming that A100s are becoming the standard kind of that everybody is using, just because there's a lot of them. They're cheap. Everybody's trying to sell you access to A100s. And hey, if you have a project, maybe instead of going to GCP or AWS, use one of these startups, right? They'll basically give it to you at a loss. So they're losing money and you're getting a better price. And then once they finally run out of money and they have to shut the startup down, then you can just switch back to AWS. Save yourself a little bit of money. Jamba is available on Hugging Face. It is meant for 80 gigabyte GPUs, so until you kind of quantize these things, you're probably not going to be able to do this on your home GPUs. But one kind of interesting thing that we discovered while kind of scrolling through here is that it seems like Mambas might have a huge weakness, and the weakness of the Mambas is that it seems like Mambas cannot be quantized. 2 different papers here mentioning the same thing, where basically they have a hard time getting Mambas to perform at a data type lower than BF16. Maybe this is what ends up killing Mambas, or maybe someone just figures out that you need to do some little modification and then it works totally fine. But as of right now, we have 2 different paths for faster inference and better performance and better, less memory utilization. One is going quantization, so using transformer architectures that are all quantized down to, I guess this is probably the limit. At some point, you might even have 1-bit language models. I don't even know what that would look like, but 1-bit language models would be crazy. But hey, if we never figure out how to quantize Mambas, that could end up completely screwing them. But it seems like they're doing pretty well, so maybe we'll see more of them. All right, that's all I got, guys. Hope you got a little something out of this, maybe a little bit of entertainment, a little bit of insight, a little bit of motivation. Thanks, Joe, Christopher, Pratyush, Khalil, MW, Snooks, Deep Tech, Emily, Divanish, El Badanos again, Falcon, Herthic, Ed, 87GN, Glass Cannon Gaming, Lee Cox, Cheb Khaled. Thanks, everybody. Hope you had a great day. Have a great rest of your day, and see you guys later.